This is an example of tidal power. It is exactly like one of the examples on your assignment, and it will suffice to introduce the topic, tell you what a tidal barrage is, and then show you what the few equations you need are. Okay, so tides are exactly predictable, caused by gravitational forces between the Earth, Moon, and Sun. You get super high tides if the Sun, Moon, and Earth are aligned in particular ways, and if the Moon is perpendicular to the Sun, you get particularly low tides. So there are two ways to harness energy from tides. You can simply put a turbine in any kind of tidal flow, and that turbine will harness the power just like a wind turbine does. But the most common way to do it is with barrages, and what that means is you take a huge dam, basically, and oh dear, and you let the water flow into a basin at high tide, and then you close a huge gate to hold the water back. You let the rest of the water, the tide, go down, and then you have a variation in height, and then you've got potential energy there that you can harness the energy from the tide. So it kind of looks like this. You have like a big dam, and at high tide, the water's up here, and this is a huge basin, so it has a huge area. A is the area of the basin, and that can be acres, hundreds of acres. And then this would be at high tide. So up here you're at high tide, and this huge barrier holds the water back. And then at low tide, which would be down here, this is low tide. Once the water has gone down outside this basin, you can then open up a gate, and you can let this water flow through a turbine, which would be in here. Okay, so this would be your turbine. The difference in height between high tide and low tide is called the tidal range. That's R. And out in the middle of the ocean, that's not usually very high. That may be up to a meter. But in some areas, like in Canada, the Bay of Fundy, it can be as high as 10 meters. If you let water run into a fairly narrow basin, you can also enhance that tidal range. Okay, so this will be in meters. Area of the basin is going to have to be in meters squared to get the units to work for us. Okay, now the power from the turbine is just as usual. So the power from the water is the 1/2 rho A U cubed. And now this is not the area of the basin. This is for the turbine. The formula we're used to. This is the swept area of the turbine blades. And U is the speed of the water. In meters per second. Now the speed of the water, if you're doing a tidal current harnessing, the speed can be as high as 5 meters per second, but certainly not nearly as high as it would be for a wind turbine. However, because the density of seawater is so much bigger than the density there, there's a lot of power available in water from tides. So remember, this is seawater, so this is 1025 kilograms per meter cubed. Okay, so that's for the turbine. And then, of course, if there's an efficiency associated with that, the efficiency goes out front there. So P electric would be eta P water. Okay, and this is what you'd use for a tidal current problem, where they give you the speed of the water. This efficiency includes the turbine, the gearbox, and the electrical generator. And then, of course, you can't harness this continuously because you only have maybe one, sometimes 2 tides per day. So the capacity factor would be in there as well. So it would be quite low, like about 0.3. 3. Okay, now if you're doing a tidal barrage and you want to know how much power is in that massive amount of water that you've held back by that dam, the formula for the tidal barrage is power in the water is equal to G rho A R squared over 2T. This is for tidal barrage questions. Okay, G is as usual 9.8. Rho is for seawater, so that's the 1025. Now A is the area of the basin, and that can be huge. Area of basin in meters squared. Now often the problems, because they come out of American books, they'll give this to you in acres. So if you need to convert between acres and meters squared, there are 4,046.95 square meters per acre. Okay, that's a conversion that you're going to need. Okay, so that's G, that's rho, that's A. R is the tidal range, so that's the distance between high tide and low tide. That's in meters. And T is the period of the tides. And it may be 24 hours, that's 1 tide per day, or sometimes like 10 or 11 hours, which is 2 tides per day. So this is the period of tides in seconds. Okay, so that's really all we need. We can actually do this example now. Let's make sure I gave you all those equations. Yeah. Okay, so let's do that example. We are told the tidal range is 4.6 meters, so that's R. So the example above. R is our 4.6 meters. A is the area of the basin, which we're told is 120 acres. So we multiply that by 4,046.95 square meters per acre to get an area of 4.86 times 10 to the 5 square meters. Okay, so that's pretty big. The period is usually given to you in hours, so it's a 10-hour period, so that's 2 tides a day. And we have to convert that to seconds, 3,600 seconds per hour. And then we have our period that needs to go in there. And so we're ready to go. Let's put these into the formula. So the electric power, and then the efficiency, overall 0.3. So we put 0.3 for efficiency. Gravitational force is what's responsible for that gravitational potential energy of that water flowing out of that basin. Density of seawater. Area of the basin. And then tidal range squared divided by twice the tidal period and this turns out to be 431 kilowatts. Okay, so that's the power available in that potential energy of water falling. If you had 8 turbines harnessing it, then each turbine has the same drop across it, and you're going to have 8 times that electrical power, 431 kilowatts. So it's 3.45 megawatts. Okay, and that's all you need to know for tidal power.